Okay, good morning, everyone. My name is Matteo Monelli from the Instituto de Astrofísica de Canarias. Sorry? It's on. Okay, sorry. I will be the chair of this session devoted to the synergy with Gaia. So before starting with the first speaker, I'll give you some reminders. First of all, recall our code of conduct. So briefly, be kind to all the other participants, both in person and remotely. And there are people devoted to receive complaints. No, we cannot see the slide, but you will know where to find them. And are there other important things I should mention? No. Okay, so let's start with the first speaker, which is Gisella Clementini, talking about synergies between Rubin-LSST and Gaia variability. Thanks, Gisella, and I leave the word to you.
Thank you, Matteo. I will switch off the video just in case, because I don't know, I'm from home, so maybe the bandwidth is not that good. Good morning to everybody. It's a pleasure to have the chance to give this talk about the synergy between Rubin and LSST and Gaia. I'm sorry, I was planning to be there in presence, but due to personal reason, I couldn't come. So I am giving this talk about variability in Gaia. I am a member of the Gaia DPAC, and I particularly work on the CU7, the coordination unit that is working on variability, doing the processing of the variable sources observed by Gaia. And I'm based in Bologna, at Bologna Observatory. So let's, I cannot move the slide. Okay, here. So this is the layout of my talk. I will give you a small recap on why variable stars in Gaia, and then we will concentrate on the products in Gaia DR3, which was published recently, and then on what Gaia can offer to LST for variable stars. Okay, let's see. Okay, so let's start by first reminding you what Gaia does. Well, what is the data that Gaia collects on variable sources. So this is an image of the Gaia focal plane. And you have the 62 CCD of the astrometric field. If you can see the pointer, there's CCD here in light blue. That are used to make the astrometric measurements, but also to collect G-band, white light in the G-band for the sources, and you have the spectral range covered in the G-band. Then there are the 9 rows of the BP photometer, prism, which does prism photometry in blue, and the 9 CCD of the red photometers. And so you can get integrated photometry in GBP and GRP, and you have the pass bands, and then the 12 CCD of the radial velocity spectrometer, where you can make the measurement of radial velocity and abundances, you have the spectra, and you have here the range. It's a small range in about 300 angstroms in coverage, where basically there are the lines of the calcium triplet. And since the BP and the P photometer are spectra, you collect spectra there and low resolution spectra there. So you also have the BP and RP spectra, and all this comes in time series mode, of course. Why comes it in series mode? Because Gaia observed the sky, all the sky, several times. And so you have more than one measurement per source over the duration of the mission. And these are typically the transit maps of Gaia for the first 5 years of nominal mission that actually ended at the end of 2019. But the Gaia mission has been extended already for 2.5 years, and which will end this year, basically, and we hope to get a further extension. Actually, there are good chances for another 3 years. So in total, the mission will take 10 years. Over the first 5 years, there has been a collection of, on average, 70 measurements in the GBP and GRP, and 40 radial velocity RVS measurements on average. But if you are in these northern regions of the scanning of Gaia scanning low, the number of observations is much larger. You can reach up to over 200 measurements in G. Now, with a survey that observes all sky and monitors the sky several times, of course, the variable source is one of the easy product of such a survey. And in fact, variable Gaia produces is producing large catalog of variable sources for which covers the sky all the way down to 21 magnitude. But Gaia also has unprecedented astrometry for most of these variable sources and photometric precision reaching 1 millimeg for the brighter sources. And what is interesting is the systematic identification of the variable source all over the sky. And the processing of the data, which is incremental, database that is incremental, the processing is cyclic and iterative, and it is improving from one cycle to the other. So this is what is done basically from the Gaia Data Processing and Analysis Consortium, that is a group of about 500 researchers and software developers spread mainly in Europe. And here you have the structure of the team. You have different coordination units, 9 in total, some of which deal with the main data, which is photometry. And in the CU5 does the photometric processing, and the data center is in Cambridge. Spectroscopy that is done at CNES, done by CU6, and the processing is done at CNES in Toulouse. And then astrometry that is done by CU3, which is in ESAC in Madrid, plus also in Torino. And then there are the coordination units that do the processing of specific sources. And what is our interest here is CU7, which does the variability analysis. But also importantly is the CU8 for the discussion we will have, which does the parameterization, the astrophysical parameterization of all the sources, and CU4 that does the study of the complex sources, like extended sources, binary system, etc. Now, with this data, we can basically have a look at all kinds of variable stars. This is a famous plot done by Laurent Ayer, which is the CU leader of CU7, the leader of CU7. And you have all the type of variable stars that you can monitor with Gaia, basically. And I will come back to this slide later, showing you what we already have in the Earth-3. There have been three intermediate data release, and the number of variables, the number of types, and the number of attributes from DR1 in 2016 to DR3 that just occurred in June 2022 has been increasing as well. Not only in the number, but the characterization of different types and the number of attributes that have been produced for these different types. And in DR3, DR3 is based on 34 months of observations. DR4, that is currently scheduled for the end of 2025, will be based on 60 months. In the DR3, there is a catalog of we have released a catalog of 9.5 million variable sources, plus 1 million AGN and QSO, variable AGN and QSO. These about 10 million sources are divided in 35 types and subtypes. And we have released a total of about 400 parameters for those sources, plus also identification of 2.5 million galaxies. And for those sources, you get astrometry, G-band and BPRP integrated time series photometry, RP time series spectra for one specific type from the long period variables. I'll come back to this later. And then radial velocities, RVS radial velocities, mean radial velocities values all the way down to the limiting magnitude achievable with the RVS, which is around 16. And also time series radial velocities and time series light radial velocity curves for about 2000 between Cepheids and Arabella stars. So here I have marked on the map on the variability tree the types. You see the white circles, the types that have been released and characterized, released in the Earth-3. Some statistic, you have here the number of per CCD measurements, number of sources that have been analyzed, because the variability is performed on all the sources that are observed by Gaia, so 1.5 billion sources. The number of variables released, And those 10.5 million variables are classified in 24 different variability types. And for 11 of them, there are specific studies. I will tell more about this later. And so 24 variability types and 35 subtypes. And on the plot on the left, you have the number of epoch over for that we in a G, that is in black, in BP, that is in blue, and in RP, that is in red. And typical numbers are around 40. But as I said, there are also cases where we have up to over 200 measurements. And the magnitude range covered by, on the plot on the right, covered by the variables in DR3, which reaches all the way to magnitude 21, the limiting magnitude of Gaia. This is the distribution for different types. So we have the largest number of variables in DR3 are pulsating stars, 34%. But then there are also a large number of rotation-induced variation, 28%, and eclipsing system, 22%, but also IGN and other types. So it's a large variety, let's say, with good numbers. Now, we know that the variable stars span the whole column magnitude diagram, and indeed the variable stars in the Gaia DR3 do span the whole column magnitude diagram. You can see this part of the diagram of the theoretical on the plot on the left. You have the theoretical image, the spectroscopy diagram, and you have the column magnitude diagram here, and this is the region that corresponds to this part. And or if you want, these are the variable stars in the LMC and the SMC. So where we really reach with the RLR is the magnitude limit of Gaia, and this is again the same part. Now, the synergy with Gaia-LSST is obvious. I mean, this is on the right, the plot on the right is the famous plot by Ivesic 2015, and where you have how the overlap in photometry, proper motions, and parallax between Gaia and the LSST. And basically, the overlap in photometry is there is an overlap of about 5 magnitudes between R16 and 20.5, 21. And there is, and of course, LSST extends the Gaia horizon by about 4.5, 5 magnitudes. And so there is this region of overlap where it is possible to cross-check, cross-calibrate Gaia and LSST. And then, of course, LST goes all the way down to fainter sources. With this in mind, now we see what we can do. Basically, what Gaia can offer to LSST. The first thing is Gaia can offer to LSST the use of catalog variable sources of different types, so source identification, multi-band light curves, in some cases also radial velocity curves, and attributes for different types of variables. Catalogs that can be used as training, catalogs to train machine learning classifiers, for instance. And also another thing that in the field of variability Gaia can offer is the software for processing and validation of the different type of variable sources, software that has been developed for Gaia, but that can be reused, recycled, adapted for the pipeline that do the classification in LSST. I'll show you a few cases of both type of problems. Let's say catalogs first, and then some software. Catalogs. In DR3, there are 11 classes of objects that have been, for which there has been a publication of a specific characterization and the publication of specific attributes. They are listed here: Cepheids, compact companion, eclipsing binaries, long period variables, microlensing, planetary transients, aurolaris, short timescale variables, Sora-like, upper main sequence oscillator, and active galactic nuclei. All the information are in this link that I provided on the bottom of the slide. And these are the numbers. So these are the numbers of sources in the different catalogs. all information, the daily information, these are the 11 types that have been studied more in the class characterized in detail, but all the information, all the 24 types can be found in this paper, Ayer et al. 2022, and with all the instructions, with all the total number of sources for all the types and subtypes. I will focus on some of the catalogs that I think can be of interest for LSST that can be used more, and the largest catalog that have been published with year 3. There is this catalog published by Gavras et al. Is a catalog made with a cross match between Gaia sources and literature catalogs. Contains about 5 million variable sources that are cross-matched with Gaia DF3 sources and represent a total of about 100 different types. But also very interesting is the catalog of long period variables there is with DF3. Is the second Gaia catalog of long period variables by Lezzetta and collaborators. And there is a list of about almost 2 million long period variables candidates. And what is interesting is that about 1/4 of these variables there is also published in the published periods, and for 1/3 of them there is also the identification as carbon stars. And this identification is done using the RP time series spectra, and this is a bad example how the technique works. Basically, you can detect, you distinguish carbon-rich from oxygen-rich long period variables using the spectra, the RP spectra, because there is this distance between these two peaks in the RP spectra that changes significantly. It's almost twice for carbon-rich sources than oxygen-rich sources. Then another very interesting catalog, and is the one of the first catalog, Gaia catalog of variable AGN, and there are about 900,000 variable AGN in this catalog, of which 21,000 are new ones, and I'm sure that Maribel Carmenero will give you more details on this in our talk on Wednesday. Now, just a quick look at the software that is used in Gaia. This is the variability processing, how the processing works. The first step is the reconstruction of the time series data, photometry, spectra, or radial velocity. Then there are cleaning of the operators, and then there is derivation statistical parameters, and then there are 3 different ways of identifying the variable sources. There is a general variability detection that then go to the field set that uses as training sets catalogs of variables, of known variables of the different types, and which is and machine learning methods. And there is a special variability detection that is done for certain specific type of sources, in particular planetary transits, short time scales, and rotation modulation offset. And then there is also an extractor for microlensing events. All these different detection methods and ones that have classify the sources, giving a probability that the source is a certain type of sources, and then the different types are fed into the so-called specific object studies pipelines, each of which is specifically tailored for a certain type. And this is where I will focus a bit more later, because we will see in more detail how, for instance, the pipeline that makes the detection of surface and aerolarity, the detection, actually the validation of the surface and aerolarity that are detected by the classifiers is made through this pipeline, and then the characterization of those sources for the different with the different parameters and attributes. And these are the 2 papers that describe this pipeline, the specific object pipelines for aerolarities and Cepheids is the same pipeline with 2 different channels. And here, just very quickly, an overview of the pipeline, a common trunk that does the main processing for both type of variables, and then specific branch, for the aerolarities and the Cepheids. But I don't want you to go onto the details, through the details of this pipeline, you can have a look at the paper if you are interested, and all the pipeline is described in this paper, and also in a paper in 2006 for 2016 on the same subject. But what is important is the way that how we do the validation and what are the tools that we use for the validation. Basically, there is a period derivation with Long-Scarron method, then a nonlinear Fourier analysis that is done independently on all three possible photometric bands of Gaia, and also on the radial velocity data when available, time series when available, a Fourier decomposition, and then as tools to validate the classification of these sources and to derive further attributes for these sources, we use the period luminosity and period ascendant relation in the Gaia bands calibrated on Gaia parallaxes for the Cepheids in particular, and use for period amplitude relation and Fourier parameters versus period relation for the RLIs. So with this pipeline, this specific object pipeline, and with the other pipelines for other specific objects that have similar structure, but different, of course, different tools and diagnostics, we produce then the final catalog that are released with Gaia. And in the case of Cepheids and RLIs for year 3, the catalog of Cepheids contain a total number of about 15,000 confirmed Cepheids, of which 900 are new Cepheids.
Gisella, excuse me, 5 minutes, please.
Okay, sure, I'm quickly finishing. And here you have the subdivision in different types for the classical, anomalous, and type 2 Cepheids, and also the other parameters that are published for those sources: metallicity, effective temperature, gravity for computed by CU8 for 1,000 of them, and the radial velocities, time series radial velocity for 100, and where they are located, the number broken down for systems. And the same, the distribution, for instance, on sky of the Milky Way, classical Cepheids, or the LMC and SMC Cepheids, and the Fourier parameter amplitudes that are used for the characterization and classification of these sources. Same numbers for RLIs. We have 270,000 RLIs in different types, and about 1/4 of them are new discoveries. Different types, first overtone, fundamental mode, first overtone, and double mode pulsator. The parameters that we derive, metallicity, absorption that we derive from the Fourier parameters of the light curve, the quantities, radial velocity curve, and where they are distributed. And of interest, for instance, is these light curves that are at the limit of Gaia, which is where actually we are really getting advantage from LSST, because we have magnitude 21 in Sculptor, for instance, are the RLR sculptor that Gaia can reach, and that Sculptor will observe, that LSST will observe much better, and also in the other ultra-faint dwarfs like Tucana 2 and Phoenix 2. These are the relation, the period, amplitude, and Fourier parameters that we use for the classification of the RLRs, and these are the distribution of sky of the RLRs in the year 3. You can see the two Magellanic clouds, the bulge reach of RLRs, and the Sagittarius dwarf spheroids and the stream, and also those little blobs that you see all over. Those are other systems like dwarf spheroidals. And for globular clusters, there are 95 globular clusters with RLR in 95 globular clusters in this map, and 7 dwarf spheroidal and 16 ultra-faint dwarfs. The metallicity map that we derive for the RLRs, and the absorption map. So all this information can be used to help LSST to do the identification and classification of sources in the data stream. And in fact, we are already planning to contribute some software and work on this field. And there is an in-kind project on this with title Tool for Classification, for Characterization, and Validation of Variable Sources. And with this, I conclude.
Are there any questions in the room? Do we have question on the Slack channel? Well, in the meantime, I have a question for you, Gisella.
Yeah.
So, a general advice from the lessons learned from Gaia. What do you think is the most important things to take into account in the whole process of managing such a huge amount of data in the process of identifying, characterizing, and classifying variable stars? Because there is a huge effort now in the LSST community.
I would say that something that we are starting to do now in Gaia, and that I strongly recommend to do since the very beginning in LSST, is a cross collaboration with the different teams. I mean, actually in Gaia, as I said, there are the different CU coordination units working on different data products, basically. So what is important is to have a feedback between the different data products that are being produced. So an exchange. I don't know whether this is already in place in LSST, but from what I gathered from the discussion that was done previously, maybe there is somebody that does the classification and then, or somebody that does the detection and then nothing is somebody else that does the classification. There should be a good interface between the different teams and groups. And the feedback should be important. It's very important. We are starting this now, inter-CUs processing, what we call inter-CU processing, and that's very useful.
Okay, great, thank you. Other questions? Well, I have a second one then. Okay, Dragana first.
This is maybe a question to both the Gaia team, but also to the Rubin team. I mean, is there any interaction between the two data management teams in terms of like sharing experience, lessons learned, and so on? It's the question to everyone, basically, but also the.
Well, if I can answer, well, I think at personal level, I think there is interaction because some of our, well, I'm in Gaia, but I'm also involved in in the Italian contribution to the LSST, for instance. That's an example, and I'm pretty sure that there are other examples like that. What I don't know if there is an interaction at higher level. That's something that I don't definitely know. And of course, in terms of Gaia data, there is a data policy that Gaia data go public as soon as, at each release, basically, so anybody can use them, but not in advance of releases, data and data products, of course. I don't know if this answers your question too.
We have a reply also here in the room.
From the Rubin data management side. So our project manager for data management is Will Oman, and the data management scientist is Leanne Guy, who's giving a talk in the Rubin Euclid session right now. And they both worked on the Gaia mission. And there's a handful of other people who are now on staff at Rubin too. So they would be good people to have these conversations with.
Thanks. Okay, I have a second question, and it's related to those 5 magnitudes of overlap between Rubin data and Gaia that you mentioned in your talk. So talking about variable stars like Aralire and Cephid in terms of distance indicators. So do you think that the astrometry and the time baseline provided by the LSST can improve the distance in that magnitude range for those distance calibrators?
Well, one point I think I can answer this your question with a consideration. What we expect from the extension of Gaia in terms of from 5 to 10 years is a gain in precision of the parallaxes and proper motions of 1/3, something like that, 20–30%. Now with LSST, of course, it is a different point. It really depends how the astrometry of LSST compares, which is a mission on the from the ground, with astrometry of Gaia, which is from space. So honestly, I don't have the exact answer to that question. I think we should check. I mean, since the astrometry of Gaia is already available for the sources that overlap, and when the first real data come out, that would be a good test to make.
Okay, thank you. So if there are no more questions, we can thank Gisella again. And we can move to the second speaker of this session. Elena, are you there?
Yes, I'm here. I'm switching on microphone, camera. Shall I share my screen?
Yes, please.
Okay. I don't know if you see it. Let me know if anything goes wrong. Okay. Can you see it?
Yes.
Okay. So I will start. So I will pick up from what Gisella said so far. She was mainly focusing on variables, of course. So I will try to give more details, if you wish, on all the data products that Gaia produces, and I will focus now on constant sources. But you always keep in mind that Gaia samples the same region of the sky multiple times. So everything that is valid for constant sources will also be valid for variable ones, as Gisella already pointed out. So let me start by presenting Gaia DR3. You see here this promotional slide by ESA. It shows a bit of the data products and the figures in terms of number of sources and so on. It's not complete, of course, it's just to give you the feeling for it. You can find more information in the release papers here. Basically, Gaia has periodic releases, but given the complexity of the data, the releases are not annual, and they are not even biannual, in the sense that, for example, Gaia DR3 was split into parts, the early release and then the final release in June this year. The release was based on almost 3 years of data, and there were several new data products. What happens with every release? You have a new data products, you have more sources for the data products that were in the previous releases, and you also have a quality improvement because each source has been observed more times, right? So what happens is that we are going to have Gaia DR4, which is based on 66 months of data, which is more than 5 years, and it will be published, let's say, not earlier than 2025. And then there will be what is the final legacy release with all of the nominal data and the mission extensions. You know that the nominal mission duration was 5 years, but there have been extensions. The first 2-year extension has been approved and is now running. So Gaia is observing its first extension. A second extension is in the approval phase, and there is fuel for maybe 10 years, fuel and coolant for maybe 10 years. So complexity is the key, no? I will, how can I change the slide? Okay. I will talk only a little bit about astrometry. Astrometry is the main goal of Gaia, and the reason why we have photometry and spectroscopy is mostly to improve on the astrometry and to improve on the kinematics of the stars and the objects that we study. Probably everyone by now knows what is the astrometric content of Gaia. You can see here in this figure the kind of formal uncertainties that we reach for objects. You see in the mid-magnitude range, we are of the order of 20 micro arc seconds in parallax. Gaia is not designed for super bright stars above the 6th magnitude, so you see the performances decrease a little bit, but it's still quite impressive, I would say. And the fainter stars, of course, have a slight degradation in performance. The similar plots can be found for the proper motions in this paper here. But what I wanted to focus on in this only slide dedicated to astrometry is that some people, especially the ones studying distant objects, have been shied away from using distances derived from Gaia parallaxes because of the systematics. You know that, or what I mean, they are called bias in general. So you know that Gaia is the only space mission all sky with very high quality that does absolute astrometry, right? And doing absolute astrometry, of course, there are biases, but these biases are well known and quantified. Because you can, for example, use quasars to study the bias, and you see in these top plots here the large scale bias in DR2 and how it has diminished in DR3. And you can also use a smaller region of the sky to study the mean motions of stars in the Magellanic Cloud and study the small scale bias, you know, this cushion shape that is becoming less intense in DR3. So with every release, we learn more about the bias, and we do a lot to diminish the bias itself, but we also do a lot in characterizing the bias. And as a matter of fact, you have the Gaia tools, which are Python programs available online on the Gaia is a website that you can use to characterize and remove the bias. So in terms of astrometry, I would say that for the moment, Gaia is unrivaled. What I wanted to spend more time about instead is the other products, which are photometry and spectroscopy, and the derived products such as stellar parameters and the like. In terms of photometry, you all know by now that we have three main passbands, the G, BP, and RP, that the precision of the photometry obtained by integrating these passbands is of the order of a millimag, in the best case, 1 millimag, which is 0.1%, while the accuracy of the 0-point calibration is of the order of 1%, which is also quite unprecedented in the panorama of large surveys. Now, if you combine this, the distance information coming with parallaxes and with the reddening information coming from other sources that I will discuss in the next slides, you have the opportunity of creating absolute and irredented color magnitude diagrams with Gaia. You see here nice examples of nearby globular clusters. Even if they are crowded, this is the quality you can get, which is competitive with the ground base, and in some cases also with HST photometry. And here you see the open clusters in which you can see a lot of details such as blue stragglers, binary sequences, and the like. And one interesting fact is that having so many stars, almost 2 billion, with such a high precision and accuracy, it is possible to detect previously undetected but predicted features of the color magnitude diagram, like the Zhao gap. You see this stripe with less star counts in the lower part of the main sequence of solar neighborhood stars. And this is the region in which stars transit from being fully convective to being partially convective. And this was predicted but never observed. I mean, we didn't have the statistics to support the robustness of this detection. So photometry is also very interesting in Gaia. But the integrated photometry, the GBP and GRP, come from low resolution spectra that also Gisella mentioned. And you see here how the spectra vary with magnitude and color for a sample of objects. These are the mean spectra for each source. You see for the very red stars, and here you see molecular bands in the spectrum. So these spectra contain much more information than the integrated photometry. And in DR3, for the first time, we made use of this information. Just as you have seen for the variables, the first time a new data product is released in Gaia, it is released in small numbers of very carefully verified sources. So in this case, we're talking about stars brighter than the 17th magnitude approximately in DR3, and no time series, just mean spectra. But in DR4, there will be, of course, for all the sources that are validated, also epoch spectra. And we hope to go fainter than the 17th. There are tools to manipulate the spectra because they are not, I mean, you can imagine billions of sources, even if the spectra are tiny, the space occupied by this data is huge. So to save space, they are represented as a series expansion of basis functions. So you get the coefficients. And you can manipulate the spectra with the tools that are made publicly available on the Gaia web pages. So one thing that you can do with this spectra is synthetic photometry. So you can pass your favorite passband on the spectra and get photometry in whatever system you like. For example, you could do this by using the Gaia XPy tool with your LSST passbands. I'm pretty sure somebody has already done that. With the LSST passbands and predict how the stars observed by Gaia would look like if they were observed by LSST. In these plots here, to give you a feeling for the quality of this synthetic photometry, I'm showing you the pre-computed Johnson-Kron-Cousins magnitudes and colors. And you see here a color magnitude diagram of the best sources and a color diagram. You see the amount of details, substructures in all sequences, the binary sequence here, the RGB bump, the horizontal branch, and all the like. And in the color diagram, one feature that, in my opinion, really shows the power of these synthetic magnitudes is how well you can separate the white dwarfs of the DB and the A type. Here, you see very well separated sequences. So this synthetic photometry comes in pre-computed catalogs in the most widely adopted systems, but also with a tool to compute your own synthetic photometry in the system that you would like to explore. The third instrument, which is the higher resolution spectrograph, the RVS, as it is called, has a resolution of 11,500, is on the calcium triplet region. So it covers, this range in wavelengths, and you can see the amount and variety of features that is visible for this specific solar type star. In DR2, you see the Gaia scheme in the DR2, there were 7 million stars with the first release, only being the largest catalog at the time. In DR3, there are 33 million stars with radial velocities measured and with line broadening estimates, so the V-Sin, which can also be very useful for certain applications. And the uncertainty is, in most cases, below 1 kilometer per second, except for the faintest and the bluest stars, because the bluest have less features. And in DR4, there will be also radial velocity time series for all of the sources. I mean, this is not as deep as the full Gaia catalog, because the higher resolution implies that we have less photon in each beam. But you see how it improved from DR2 to DR3. It's almost a 2 magnitudes improvement. So we will see what happens with DR4. It could be a similar type of improvement. You can find all of the simulations on the Gaia pages and more details in these papers. So to go deeper than Gaia with radial velocities, there are spectroscopic surveys that are specifically designed for this, and more are coming, like WEAVE for most moons and the like. And there are projects like the Survey of Surveys that homogenize all of these catalogs in one reference, which could be very useful for LSST as well. So with this type of spectra, I do not only measure radial velocities, but in this simulation here, you can see for stars of different types what are the atomic lines and molecular lines that can be used to derive abundance ratios. So you can really characterize the stars with this type of data, similarly to what was done by the RAVE survey. So in DR3, you have a little bit less than 6 million stars with the same magnitude distribution as the radial velocities that I was showing you before, with some element ratios like calcium, titanium, silicon, and the like, and all of them with temperature, gravity, and metallicity. The comparison with the literature show that these parameters, especially temperature, are super reliable, but of course, metallicity and gravity, when compared with surveys with higher resolution and wider wavelength coverage, show some systematics. So some formulae are produced to correct for these systematics, and you can find more information in the papers listed here. Now, of course, the next release will take this into account, all the lessons learned, and more stars with a higher quality will be published. But we do not only rely on the high resolution spectrograph, we can also derive parameters from the low resolution spectra, and also from parallaxes and all of the information that Gaia provides. And you can see here, this is the work in Gisella's scheme of CU8, which is the CU that classifies and parameterizes objects. There are many different data processing modules focusing on different regions of the parameter space, on different types of objects. And here you see a dictionary of where each module operates best. And in the R3 of the magnitude distribution and region of the temperature and magnitude plane that are covered by each module. If you focus in particular to the GSP spec, which is the one which derives parameters from the RVS that I just showed you, you see the GSP spec in green only goes down to the 14th magnitude, right? Because it uses RVS data, while GSP FOT is, of course, less accurate in general, especially for metallicity. The metal poor stars are not classified well, but comparable for temperature, for example, and you can go down to the 18th, 19th magnitude. It's the orange line. So using just the BP and RP spectra, okay? So the catalogs here are super complex and super rich in information, and it is really worth investing time in studying the content, because not only temperature, gravity, and metallicity are produced, and stellar classification like galaxy, quasar, binary, variable, hot, cool, and the like, but you also have, with the help of theoretical models, the stellar mass, the stellar luminosity, the stellar radius, the stellar age, and extinction and reddening. And in particular, concerning extinction and reddening, I think it would be useful for the people studying variables to know that in Gaia, we do not only estimate that for variable stars from the light curves, but we also have independent ways of determining it. Of course, from the BP and RP spectra, you see here for solar type stars, how the extinction varies with the spectral shape, which gives us a handle to derive a reliable extinction estimate. But in the RVS, we also have the diffuse interstellar bands, which are absorption bands of presently unrecognized molecules in the interstellar medium, which scale very well with reddening and extinction. So we can use them to create reddening maps. And as a matter of fact, since the year 2, Gaia provides extinction and reddening for each star for which it was possible to compute it. And these maps talk very well with the 3D maps available in the literature. I mean, the main disagreements with the maps such as the green, the Lallemont, and the other 3D reddening maps are in individual regions of the space or for individual sources. This is because Gaia doesn't go into the infrared and doesn't go into the ultraviolet, so we only see the optical part of it. But still the numbers compare relatively well with these surveys and can be used. And with each release, of course, they improve. Another thing I wanted to point out is that apart from the astrophysical measurements, Gaia provides a large variety of quality indicators and flags. And these quality indicators and flags are able to enable a large variety of scientific applications. You have probably heard about the famous RUVE, which is the renormalized unit weight error, which is related to astrometric excess noise. It basically tells us if in deriving the astrometric solution for a source, higher than average disturbance was found, indicating, for example, a binary companion, variability of the photocenter for quasars, the presence of a faint trace of the galaxy host for point-like unresolved galaxies, or disks for nearby stars, and the like. So it's a super useful indicator that was employed a lot in the literature already. But there are less known indicators, such all of the ones concerning the image parameters determination, so the processing of the PSF and LSF of each object. One of these is the frac multiplic, as the fraction of objects which appear double or multiple. So if a source has more than 10% of the transits in which it appears double, it's a good indication that it has a nearby companion, and this identifies companions between 0.2 or 1 arcseconds of separation, and it was used in this paper in Nature to find a large number of double quasars and gravitationally lensed quasars, for example. It can also be used to separate nearby companions. There are other means, but it's pretty simple, straightforward, and effective. And there is also the BP and RP excess, which is a comparison between the flux in the G band which is an image, so it's the space quality PSF, and the flux in the BP-NRP, which are little spectra that extend for 2 arc seconds. So if the sum of the flux in BP-NRP does not correspond to the flux in G, it means that there is a source between, let's say, 0.7 and 2.5 arc seconds that can contaminate the flux and can be used to remove contaminators in this way, and also to find galaxies separated from stars, and so on and so forth. So using these indicators, investing the time to study them and understand which ones are useful for your goal can be pretty rewarding, in my opinion, and should not be neglected. The last topic I wanted to talk about is non-single stars. So as Gisella pointed out, each of the instruments, astrometry, spectrophotometry, and spectroscopy, observes sources multiple times during the mission duration. And so this is used a lot for people studying variability, of course, but it's also used to study binaries, because we can have a radial velocity curve, a flux variation, and in this case, you have an eclipsing binary. You see here radial velocity, G band, BP-NRP. You see the 2 eclipses, and you see how TESS sees this source. Of course, the Gaia sampling is sparse compared to a mission that is designed for following this type of objects, right? But one interesting fact is that the eclipses do not occur in the same position, because TESS is observing in another time window. And so this shows how the system has evolved with time. And so it can be combined, TESS with Gaia, and similarly for astrometry, Gaia with LSST, to increase the time baseline for the study of this type of objects. You can find more details in how the astrometry, photometric, and spectroscopic information is used to identify and parameterize binaries by deriving orbital periods, separations, classification, and in the fortunate cases, the masses of the primary and the secondary, and so on and so forth. And I think this...
Excuse me, 4 minutes, please.
Yeah. Okay, no, I finished. This was my last slide, so I only have the conclusions. So this is all to illustrate how complex the data Gaia are, but rather than using the word complex, one could use the word rich. So if you're not scared by the richness and the time to navigate the documentation and to test a little bit about the power of each of the information and data types provided, I think this can be pretty rewarding, and it can be used, and I'm pretty sure it's already being used, to plan the LSST observation strategy, data processing, and especially the validation, and possibly, as Gisella and others mentioned today, to combine the 2 data sets later to increase the time span and the amount of science one can extract from the combined data sets. But most of all, I want to encourage you to use the data, have fun with the data, and in doing so, I thank you for your attention. Should I stop sharing now?
Thank you. Are there any questions here in the room? Question? No questions. There is a question from Slack by Will Clarkson. So thanks for a great talk, Elena. Can you say a bit more, please, about the improvement in accounting for spatial confusion we can expect in DR4? Spatial confusion? It means resolving multiple sources, overlaps, crowding, and this type of things. I think so. Okay. So I have something here in the photometry part. So what happened is that, especially in the BP and RP spectrographs, because these are dispersed images, and so they are a bit longer than the G images, you have in crowded areas such as globular clusters, the disk of the Milky Way, and specific regions in the sky, you can have crowding effects, right? And what happens, well, I didn't put everything in the slides, but we have several tools we can use. For example, astrometry is much more spatially resolved than spectrophotometry. So we can use this and a specific software, which is called the SEA pipe, Source Environment Analysis Pipeline,
to reconstruct around each source what are the possible contaminating sources. And once we know that, we can decontaminate the spectra. So what happened in DR3 is that we used the scene reconstruction for the first time, not to decontaminate the spectra, but to remove those transits that are contaminated when computing the mean magnitudes, right? So we already have an improvement in the crowded areas compared to DR2. In DR3, instead, we have several modules for contamination, blending, and the like, in which the scene reconstruction will be used, profiting from the fact that we have several transits with different orientation on the sky, to use the scene reconstruction to de-blend actually the BP and RP spectra from each other, okay? And all of the indicators that I was mentioning, the RUVE, the IPD-FRAC multi-peak, the BPRP excess, will be used to select which sources need this specific treatment to improve not only the photometry, but also the astrometry itself. Because once you know for sure that these are two sources with a certain magnitude contrast and with a certain spatial arrangement, you can also treat them astrometrically in a different way. Okay, so this will all start happening in DR4. In DR3, we had just a preliminary treatment to get cleaner integrated magnitudes. I hope this was what was asked.
Yeah, thanks. Other questions? Well, I have one for you, Elena. It's about the synthetic photometry presented in the Montegrifo paper. So do you think that synthetic photometry in the Rubin filters passband could be useful for calibration purposes or monitoring 0-point variations, for example?
You mean using synthetic photometry in the Rubin filters on the Gaia data to compare with the LSST one?
Exactly.
I think so. I think so. I mean, as long as one is careful enough in standardizing the magnitudes to make sure, no, that everything is on the same scale, this could be extremely useful. I think that the same, well, almost the same mag precision and less than 1% accuracy can be obtained for the synthetic magnitude if one is careful enough and knows what to do.
Okay.
So yes, I think so.
Okay, great. Thank you. So no more questions. So let's thank the speaker again.